Can you confirm recording is there? You got something and you have to click OK or nothing. This is okay. I'll just say recording is on. Okay. Hi everyone. Welcome to the IEEE Future Networks webinar panel on QKD or quantum key distribution. Today it is September 25th, Thursday, 9 a.m. and we begin the session. Everyone is welcome to add their questions if they have any in the chat window, which is what we'll use for everything, hopefully. And as part of it, most of the folks will be muted, and only the speaker and probably one or two people maybe in the panel, will let them talk as they, but as long as you maintain the silence, that will be the key. So with this, I will hand over the start of this to our co-chair, which is the Quantum Information Technology QIT co-chair, Chintan Oza. Take over, Chintan, and let me know when you want me to move the slides.
Thank you so much. Hello, everyone. My name is Chintan Oza. I am the co-chair for Quantum Information Technology Work Group. Welcome to this webinar. We are going to have a webinar. We are going to have a webinar on quantum key distribution today. Indeed, this is a subject which we were planning since long. We have been planning various activities, and this webinar is long due. And thank you so much for fellow panelists and Prakash for leading this activity. With this, let's move on to the next one.
Are you able to see the?
So yes.
Yeah.
Let's move on.
Yeah.
Yeah. So indeed, it's my pleasure to welcome Dr. Nikhil Rajput, Professor Vipin Rathi, Professor Jayanti Gokhale, Dr. Radhika, and Prakash. Thank you so much. Thanks for joining in. Let's move on. So at this point, it is indeed important for all of us to thank and extend a note of gratitude to all our collaborators and sponsors with whom we have been collaborating from time to time. So this year is we have IEEE Philadelphia section, IEEE Computer Society Philadelphia section, Emerging Open Tech Foundation, INGR Security and Privacy Working Group, INGR EIML Working Group, and IEEE Future Networks Community. So let's move further. INGR has got several working groups, and QKD involves terrestrial and non-terrestrial communication. We like to acknowledge their roles on providing information for us to leverage the portions we use from their research. In particular, optics and satellite satellite need for the QKD and MFC and SETCOM. So the link for respective work group has been given. So we extend, I would say, a note of thanks. With this, let us move to the next slide, please. A note of gratitude to them. So I have been adequately introduced, so we will move on to the next one. So this is the composition of IEEE Future Networks technical community. We have 9 sponsor societies. This includes OPSOC, Electronics Packaging Society, CAS, ITS, MTT, IEEE Reliability Society, SSCS, VTS, etc. We have three major events: IEEE Future Networks World Forum, which is called as FNWF. This year it is being held in Bangalore, our IT capital city of India and world. We also co-host IEEE Connecting the Unconnected, and we are the first work group to have first responders and technical networks specialized for 5G. Apart from this, we also do various types of research and education activities where e-learning, webinars, distinguished lectures, and white papers as well as tutorials are published. Next slide, please. So this year, as I just mentioned, IEEE Future Network World Forum, popularly known as FNWF, is being hosted from 10 to 12 November in Bangalore. You can check out their website fnwf2025.ieee.org. I look forward to meet all of you at the FNWF. On this website, you'll also find various key dates as well as guidelines for booking your hotel as well as travel. Next slide, please. So these are the deadlines for IEEE Connecting the Unconnected. Next slide, please. More information can be viewed on ctu.ieee.org. This is the broad IEEE INGR structure and various working groups. You can visit futurenetworks.ieee.org/roadmap. It gives you a fair idea about the roadmap which is being pursued by various work groups within IEEE INGR. Next slide, please. So IEEE INGR has shared the strategic vision and technology roadmap in various phases or various work groups. So if you look at this slide, the strategic vision and advancement to humanity through technology is being, pursued by 15 different work groups. They are focused on technology and society. Work groups target key areas across technology and societies. They also publish various documentation. You can visit this page of future networks and then have a look at the publication by various work groups. Next slide, please.
Are you seeing the stack?
Yeah, I guess I would request you to take over from here.
Okay, so what we have is the QIT working group. Prakash, I am the co-chair along with Chintan. This is the quantum information technology, we call it. Initially, we started with quantum information and communication because it involves compute and communication, and it is represented by different society like CAS, which is nothing but a design for the various semiconductor technology and all. Therefore, this includes computation, communication and sensing. Integrated communication and sensing is the key for the qubits. And you have the hardware, the operating system, compiler, interpreter, languages, and the framework and algorithms and applications. So this is the level of abstraction, bottom to top, for a stack for the quantum, which is along with the von Neumann architecture, as we call it. This is along with that, we are also including in that the analog portion of which is quantum at the bottom. So you have three basic principles: superposition, entanglement, and teleporting. Those are the three key which as we go we will be explained, but at this time you remember these are the three keys. Superposition is simple, which you combine the two, and if you have waves and you combine the two, you get the sum of the two. You can a plus b, b plus a, all these are equivalent, something like that. But this is at the not at the bit level, at the qubit level, which can be a 0 or a 1 at any given time. So that's the simple. Qubit is what drives at the center, and you have the various electronics able to support that, and on top of that is all your so quantum stack is important to understand. We will go with that. So what QIT group has done is we have done several areas in the application, like we had previous one, post quantum cryptography, and prior to that we did QML. So we work with the various groups: AIML for QML, security for the what you call the post quantum cryptography, which is shown here in terms of, and then lock and key types, which is for encryption, decryption, and all that we did last time. Now we have moved to quantum key distribution, and this is one research RAQR, which is Rydberg Atomic Quantum Receiver, which is coming in the 6G era. And let's see how it gets in, but that's based on laser, etc. So I'll just say that there are many things in the QIT group we do. Main three things are computing, communication, and sensing. So computing, we want that to be a utility, fault tolerance, scaling, and we can do it for simulation of twins and all. Quantum communication, integrated communication, and sensing. This is for PNT, we call precision and navigation and tracking, and quantum sensing, which is weather and etc. etc. So we want the terrestrial and non-terrestrial interoperation. That's the key goals of, and we are on march towards the IMT 2030, which is the one, and these are the three areas as I mentioned: integrated sensing, integrated networking and communication, and quantum computing, and with the CPU, GPU, QPU as clusters, and most of them are moving toward the DSP chips. So we are planning for Chintan, I will leave you here. Go ahead. Chintan there? Okay. If
Yes,
not,
sir.
I'll
Yes,
just
sir.
go ahead.
Yes, sir.
Survey.
Yeah, sure. So this year we are going to publish State of Quantum Computing 2025 report, and to facilitate this, we are going to launch a survey. So with this, I mean, stay tuned for various media posts wherein you would look for the link for the survey. And the goal of this survey is to find end users and quantum builders participating there. Participating and sharing their views on how mature the technology has evolved around them in last few years. It is also important with the state of quantum computing report, we document that what do they see in next 1000 days, how technology is shaping up various types of pilots right from lab to market. Now, 2025 being the year of quantum computing, many use cases are now moving beyond the lab, and that is where I strongly believe that this report is rightly placed and it would be getting an informative and insightful outcome for all of us. So, my request to all of you is please help us to get maximum participation in this survey. I request you to kindly share it with all like minded people so that we get maximum answers and our data set is wide enough to get the better, varied inputs and thus a accurate answer or trend. Next slide, please. Thank you so much, sir.
So we have Dr. Nikhil Rajput here. Is he there, More?
Yes, Prakash. Yeah.
Okay. Oh, Nikhil is there. Very good. So his introduction, one of the most, what you call, uh, behind the scene guy I have seen in ages. He's a very quiet, humble person, and he has got varied, like he has BSc in physics, he has got, BSc in math with MSc in physics and MTech and PhD, and a well-versed and professor, and he has been key player in the Linux Foundation along with his colleague Vipin Rathi. They have been really very uh, ag- aggressive, but this is like you have two, out of which one of these guys is the silent guy behind the scene operator, and Vipin who will follow. He is the one who goes in front. Both of them have been really taking up challenges in and out. They operate from their Ramanujan College, Delhi University, so RCTU we call it, and they have been part of the national missions on different education to quantum to semiconductor, and with we hope they will be able to get to the limelight as they mature. They are definitely the key players in Indian scenario. And with that introduction, I will let Nikhil handle starting with the architecture of QKD. Nikhil, go ahead. Thank you.
Thanks, Prakash, for the introduction. So, I will talk about the fundamentals of QKD. So, actually, quantum key distribution leverages the principle of quantum mechanics to establish secure cryptographic key between different parties, so that the key exchange is secured, and it utilizes the basic architectural design you can see in this diagram. They are different. So we have a sender and a receiver, and you can see there are two channels here. One is a quantum channel and the one is a classical channel. So quantum channel actually handles the key establishment phase. uh, this is where we are dealing with single photons, and we also use deal with quantum state preparation and its measurement. And again, it utilizes different quantum mechanics principles. From engineering perspective, we can say this handles like range limitations, temperature sensitivity, and extremely low error tolerance. So all these are handled at this quantum channel. And the other channel, you can see that there's a classical channel which handles everything else. Like there's a thing which we call as shifting, SIFT, error correction, privacy amplification, and even the authentication. So these things are handled at the classical channel level. And this is where also we can leverage existing telecommunication infrastructure and protocols. So classical channel is where where we actually connect with the, we can say, our laptop, or whatever the classical methods we are using, that is utilized at this channel level. Also, you can see this separate architecture allows us to, actually utilize the feature of the quantum channel, as well as, the existing channel can be used along with this quantum channel. So this, you can see other parts are simple, like, we have transmission module, receiver module, and, quantum link. Generally, it is of 1550 nanometer, and classical channels can be fibers with different wavelengths, or separate channels also. So yeah, let's move to the next slide, please. Okay, so this is QKD with relay architecture. So what it basically solves the problem, that relay architecture actually addresses one of the most QKD's fundamental limitation, that is range. Because you cannot connect to a long range directly, so we need some kind of distance. Also, QKD with relay is one of the solution. Direct quantum links are typically limited to 100 to 200 kilometers due to fiber losses and detector efficiency. Architecturally, this introduces a critical design decision that we call as trust model. So with this trust model, the relay node, as you can see at location 2, it must be trusted because it accesses both this KR1 and this first location of KR1 and KR2 it location, so it accesses both the things. That's why we need trust network and trust nodes here. From implementation point of view, it means actually the physical security requirement for the relay nodes, and also key management protocols that handles multiple hop scenarios. It also handles the synchronization across multiple quantum links, and also it take care of this failure handling when the relay goes down. This relay architecture also introduces interesting performance characteristics. So you can see, the effective key rate is now limited by the slowest link in the chain. So for overall reliability, the product of the individual link reliabilities are, it handles that. So we can compute like that only. So this is about this QKD relay. Let's move to the next slide. I think that is blank. Yeah, no, it is okay. So again, what these are the requirements. So there are different architectures. I will, you can see few things are there, but they are different things. So in basically QKD, for a QKD system, the basic requirements are like quantum light source, which is the most essential part of it. Again, after that we need like state encoders. Photon detectors are also required because from one side this entangled photon for the entanglement photon connection, we need this single photon detector as well as quantum light source, which is generally laser. And for photon detectors, we have different kind of systems like four-way mixing, and we have also now quantum dots are also there. So there are different things which are going on, and new kind of research works are also going on in these areas. What actually, you can see there are optical switches. These enables one to many and even many to many connectivities. From system perspective, that needs to be fast enough to support time division multiplexing. Okay, for this quantum channels. And the it has also the coherence properties also need to be maintained because for this quantum communication. uh, the other things like we require like quality of service, network resilience is required, and also for we need it for scalability also. So the hardware part is I think Vipin or other speaker will cover that exact the hardware part of that. But if these are the simple requirements. So the whole architecture, it is very vast and it differs from different perspectives. So if you go for satellite QKD connection, it is slightly different than miniature form of QKD. And nowadays, I just read about that Singapore. In Singapore, this chip-based QKD is also being developed. So different, because and different kind of protocols are also used. I think that will be covered. So let's move to the next slide. Yeah, so this is the QKD specs. You can see there are different things, and one of the major thing is the protocol. So in general, you will see that BB84, E91, and you can see this COW protocol. These are used, and with BB84 the oldest one, so that protocol is still used, and with some modifications like require states and other things are there. And other components are like things you can see here, like as I mentioned in the previously that we need a single photon detector. So here you can see this avalanche detector is used. And even this the second one, the SNSPD, is another kind of detector which is used in the QKD system. And other things are like we need RNGs also. So nowadays you can see that people are using QRNG. They are also they are trying to use the TRNG, which takes intrinsic noise and other factors for the generating random numbers. But now, QRNG, and even you can see that entangled based QRNG are also there. So these are also used here. And we need a different kind of control systems also. So these are the specs, and these specs differ for different kind of system. As I mentioned, that we have now satellite based QKD, in not the normal air-to-air QKD systems, and even the satellite based, like China has launched, I think 2 or 3 years back, that Mischief satellite that uses this QKD principle, the entangled photon concept principle, for connecting. It, I think it established the connection from about 500 kilometers, as I can remember that. But yeah, these specs, there are a few factors that is required for every kind of QKD system. That is, you need to reduce this QBER, the error rate, and the main challenge is to decoherence, to prevent the decoherence, and maintain the main thing is, like the QKD system, it should be in the room temperature based. So most of the systems which are there nowadays, that uses different ions and superconductors and other things, so they require the temperature which is very less than the room temperatures. So these specs differ, and people are working in different directions. As I said, chip based QKD is also going to be in the picture very soon. So this will change the whole QKD environment, and it will make this quantum communication possible, the real possibility, where we can use actually this for our daily communication. It will take some time, but I think we are moving ahead in that direction. So I think that's it from my side. Yeah. I think
So,
Vipin will cover this. Yeah.
so Nikhil, can you introduce Vipin? I will leave that to you. Thank you.
Yeah, I think you can introduce, because you know him from a very long time.
I can introduce myself, by the way.
Okay.
Okay,
So, just to put it, he's a 5G expert, but at the same time, a lot of things he has done along with Nikhil. So, his topics is here, but let himself speak for himself. Go ahead, Vipin. Vipin, are you there?
Can you hear me? Hello?
Yeah, we can hear you. Good. Go ahead, self-describe,
So,
self-introduce. We cannot hear you.
can you hear me? Hello?
Yeah, go ahead. Yeah, we can hear you.
Yeah, hello. Yeah, so,
Yeah.
I think there's some issue with your microphone, Vipin.
okay, just give me a second.
Yeah. So while he
Can you hear
works
me
on
now?
his microphone, yeah.
Yeah.
I know Nikhil for several years. He was on the board of OpenStack as a executive, and so as a board member before. After me, of course, I was doing earlier, but he has been with the Linux Foundation as the chair for Hyperledger, and he's one of the. He was a Google scholar. He has worked in the what do you call the labs in Switzerland, and he is at the CERN, and obviously he and Nikhil almost joined the same day, I believe, at Ramanujan College of Delhi University, and they have been handling quite a bit of educational aspects of various technology, as well as advising the departments and ministries. So I think both of them have been, and they are even working on the 60 as we speak. So they have even worked on the device drivers up to. So they have got full stack coverage, and they have been handles the 60 lab. He established the first 60 lab in university in RCDU and in Delhi University, and then they have been helping others to and work with IIT Madras and various other IITs and Delhi IIT. And so he's very colorful, very aggressive, very humble for what he is. So let me hand over to him. Nikhil, go ahead. Sorry, Vipin, go ahead. And these are the topics. Yeah, go ahead.
Can you hear me now? Hello?
Yeah, we can hear you. Super. Are you speaking? Some issues? Vipin?
Yeah, can you hear me now? Hello?
Yeah, we hear you. The slides are there, in front of you. Go ahead.
Thanks. Thank you. So before I start, I want to start with the whole this quantum infrastructure things so that we can understand better.
Sure.
So we have 4 layers. For example, we have hardware, middleware, software, and other layers on.
Yeah, I can get that slides for you if you are looking for that. Sure. This you can go ahead with this. Yeah, go ahead. Are you able to see now the stack, quantum stack to start with? We have
I
some.
think there's some issue with their his mics. Vipin, we are losing you after some time, you know.
Or do you want to have your slides? We can do that if that helps.
No, can you hear me now? Hello?
Yeah.
Hello?
Are you able to see the
Yeah.
stack you were describing?
Yeah. So I was describing the stack. So there are 4 layers. One is hardware, middleware, software, and security networks. So on the hardware layer, you can see there's a processors, there's a sensors and communication devices at the hardware level. This is where quantum devices we have, like in quantum communications, we have QKD, QRNG as a hardware components. On the middle layer, middlewares, we know that there's a cryogenics, lasers, and different control electronics, FPGAs. But on the software side, there are multiple SDKs that is available. We do QML and the hybrid HPC plus quantum as well. For example, CUDA Q or something like this. So, for example, in NVIDIA GS200 with NVIDIA GS200, you can have, I think, 32 qubits, which is simulated, right? So this kind of hybrid HPC is very, very important for QML simulations and other things. On the security parts, there we have PQC. This is QKD and different applications, for example, post-quantum VPN and data centers as well. So with this QKD, what we can do is, as Nikhil showed that how most of the time traffic goes from the classical channels only, right? So this quantum channel is like 2% of the traffic. 98% of the time we use these classical channels for these quantum communications. And this is where we need the extra security on the classical channels, which we can add PQC, and this whole combination becomes hybrid as well. Also, QRNG is needed for PQC for the better entropies. So this is like a mix once we go to the security. And on the QRNG side, just try to see in terms of software. For example, we have in Linux, there is a path dev random. So by default, this take PRNG from any operating system or from any libraries. But in case of QRNG also, you can change your paths for this dev random, and then you can directly go ahead with the QRNG integration with the PQC libraries. In the PQC libraries, you can do different kind of chems or digital signatures. There's a one way also, like we can do asymmetric encryptions, also symmetric encryptions also possible. For example, in post-quantum VPN, we can use QKD keys through, there are standards, which is in HC QKD 014, I think. You will get REST APIs from this QKD and use these keys as a PPK or PSK, different RFCs available for these integrations, that if you can use post-quantum pre-shared key in, and the applications can be VPN and other things. This is very important for air gap networks because we can't do asymmetric cryptography, right? So in most of the time, in most of the air gap networks, we use symmetric keys, and they don't want to use this asymmetric algorithm, whether it's post-quantum safe or not. So in those cases, QKD is really helpful to generate these kind of PPKs. And for PPK, there's a multiple RFCs available nowadays. On the hardware layer, as I mentioned, we have quantum processors. On the quantum communication side, again, we have QKD with different ways. And the application of QKD, we can do either drones, either terrestrial or non-terrestrial networks. On the non-terrestrial network, it can be on satellite as well. It's called as free space. And this is how the whole network builds up, right? So we need quantum processors for that, and quantum communications, and also quantum sensors is much means people are looking into. And on the software stack and the security layer, as you can see, this either you can use Qiskit or CUDA-Q or multiple quantum SDKs are available, and so simulations you can do for this QMLs. I think today only HSBC and IBM released some quantum finance algorithms through which they I think they achieve 34% better results, which is like real-time applications of the QML nowadays in various domains, whether it's fintech, whether it's telecom, whether it's healthcare, or a lot of other places as well. So we use QML for telcos, especially in the 6G. If you look at the 6G, there is a quantum communication in 6G as well. In release 20, I think they in secure SA3 and SA5, they introduced both PQC at least. Not sure about QKD. Maybe in release 21, they introduced this whole quantum communication concept in the telcos as well. So we do some QML at different layers as well. For example, for layer 2 scheduling and a lot of other use cases at layer 1 as well, to make this signal processing more greener, more faster, so that you can optimize and can save billions dollars. In India, of course, NQM is a hubs, different hubs computing, either communications and sensings. Same way, US also has their mission. EU, China, there are a lot of missions going on. Of course, there are challenges in scaling these qubits. Also, the fault tolerance is a problem nowadays. But yes, many companies are working on to improve all these things. Certification is a big problem in nowadays, and also standardizations as well. If you see like NIST standards for ACVP or CMVP, it's really hard, right? So, for example, there are only 2-3 companies in the world who got these certifications, right? So because of a lot of like, I think you have to pay $50,000 or something to get these kind of certifications. So yeah, so means once it goes in the mainstream, then it will be, I think, more accessible, and then it can become the commodity as well. Means there are opportunities, there are multiple opportunities based on the like how we want to shift, migrate, and how we want to use these terrestrial QKDs or satellite free space. For example, in free space, we tested how you can use like, for example, if I put a quantum VPN on the satellite and on the ground station, then at least we have added PQC layer without any cost of QKD and miniaturization problem of the QKD. Because on satellite, the payload should be like 5 to 10 kgs or even lesser, and there's means not much QKD available for of this sizes, right? So that's what we can do today is we can add these PQC layers over the classical channels and can secure all these communications. Of course, we can integrate PQC with QRNG, and of course on the terrestrial we can use QKD as well. So this is like a mix, right? So it's not one-stop solution for anything. So it's like what we can do today is we can start with software and slowly move towards hardware, because hardware, there's a lot of capex involved in these kind of hardwares as well. And the size of these hardwares, energy, there are a lot of issues, especially in the capex sizes. And also, if you see long-term goals, of course, we need compute. So if you see the transitions from starting from the PQC with different use cases and QRNG, and in the middle layer, you can see that QKD acceptance, and on the long-term side, of course, we need a compute. So this is like a roadmap strategy for any nation, that how they can shift. And again, there are multiple applications in banking and finance. Defense, we know there's a lot of scope. And in telcos, I think people are talking about AI RAN, and some people also tested QML. On the security side, as I already mentioned, this is PQC and QRNG integration is already started in multiple groups. So yeah, so and for the testing purpose, as I mentioned, we can use these hybrid infrastructures to accelerate adoption of the QML, because we can't use QML directly on the compute instead of on the quantum compute. Instead of this, if we can use these classical compute, especially these GPUs, and can simulate these GPUs to something like 32 qubits or 33 qubits, because that's very particular because of the states. For example, if it all depends on the sizes. For example, if you have HBM3, then it will be like 141 GB kind of things. That means 2 raised to the power 33 states, and it's like something 8.5 billion amplitudes. So that with these compute, what you can do is you can simulate your hardware, and then you can learn that, okay, what's going on, how my algorithms look like, and then you can directly go to the compute as well. So instead of directly going anywhere, for example, in the PQC as well, first start with the classical to hybrid, and then hybrid to fully post quantum. So this hybrid world is very important for these transition, whether it's compute, whether it's software layer, or any even in the FPGA side as well for the acceleration. We can do acceleration of these software layers at GPU or DPUs. On DPUs generally we offload, and on GPU we accelerate, so that my libraries go directly into these, and my CPU cycles should not be used, right, for such kind of workloads. Yeah, so this is it from my side, but this I always say that we have to plan for. We can't directly go to QKD. We can't directly go to fully post quantum. Of course, if you are using PRNG, of course you can use TRNG, and then of course in some time, once you're comfortable with the TRNG, then you can do QRNG as well. Unless you don't have these kind of roadmaps, it's really tough for migration strategies. Yeah, that's it from my side. Thanks,
Yeah,
Prakash. Thanks.
Nipin, excellent. Even though the slides were not matching, your speech presentation was super. And I would say that 6G definitely has a role, especially in the integrated communication and sensing area. Your point is well taken that you can't go like we do in migration in the 4G, 5G, 6G and all. Same way we have to have a NR, we call it, right, in the standards. So you have to go through hybrid before you can actually do the classical to hybrid to you said 2% of the traffic is in the what do you call the quantum channel right now, and that needs to be improved. And there are in US, there are cable providers who have moved from copper to cable, and they are touting as quantum internet for peering. So yes, there is scope everywhere in different regions. And thank you for your presentation. We really liked it. It really brought the essence of the commercialization, which is the key. And so with that, we thank both Vipin and Nikhil from RCDU Delhi, and we move on to next speaker. Our next speaker is the subject matter expert in the quantum, and he is going to talk on the teleporting and QKD protocols. Go ahead, Gokhale. He is from IIT Bombay. I've been working with him for long, and his focus has been on the quantum of last few years. Prior to that, of course, he was in the more on the Java side and embedded structures, and he has been advising L&T and defense organization, and so we want to hear from him. Gokhale, Professor Gokhale, go ahead.
Thank you, Prakash, for the introduction. Hello, panelists and all other participants. Once again, I thank you for the opportunity. I'm typically going to cut across this entire talk and then get down to the brass tacks, I should say. So I'm getting on to typically something like not exactly a 101 level course, but it's slightly above, just to give an indication as to what are the most appropriate, let us say, protocols which are currently in use in the QKD scenario. So today I'm going to talk on two topics, two aspects. One is on quantum teleportation, what exactly is the significance of that, more specifically leading down to a communication oriented scenario, or maybe leading down to quantum internet technologies. And after that, I'll be very quickly getting on to a brief overview of what are all the various protocols which are supported currently in QKD. I have a list of about 7 to 8 protocols, but due to paucity of time, I might be probably forced to skip a few of them. I should take about 20 minutes of time to complete my presentation, after which I think Prakash will hand over the remaining aspects. So we'll just get started with what is this concept of a teleportation. I think everyone knows about this concept of teleportation, especially if you know the core features of quantum technologies. Primarily, if at all I say that I have, let's say, two particles which are entangled with each other, using this concept of entanglement, if at all I sort of separate them out in distance, right, I can typically and still maintain this entanglement across, because of which what I can say is any state variation of one particle can be observed at the other particle. We are really not going to do any physical transfer of material or matter, and this is the core concept behind teleportation. Secondly, this is a quantum phenomena because of which it still does not violate causality, and we still assume the fact that it does not happen just instantaneously like that, but it does happen at the speed of light, right? And to support this teleportation, we primarily require a pair of entangled entities. And these entangled entities, one is handled by the sender, other one is handled by the receiver. Just imagine you have got two synchronized, two attached entities. If one changes, if at all the change can be felt at the other end, basically that gives me a very good gimbaled type of approach to send information. Next slide, Prakash. So what exactly is the overall protocol? So this is primarily a protocol for teleportation, which we are going to use in other subsequent aspects of QKD. So that is the reason I'm spending a bit of a time. Let us assume that you have got Alice and Bob. These are the two participants. These are the conventional participants in any communication environment. We assume that Alice has got a qubit. We call this as a qubit A. And the objective is to transfer this qubit A to be teleported to the Bob side. So that is basic objective. To enable that to happen, Alice and Bob typically will have, let's say, two of their qubits, right? So I give a qubit B to Alice, qubit C to Bob. So each of them now will have a pair of these qubits. Now these are entangled pairs. So now we have got three things. One is the qubit A that needs to be teleported. That is with Alice. Alice and Bob together share a pair of entangled qubits. And because they are entangled, they obviously are in a Bell state, and that is a mathematical representation of a Bell state. So what we now do is something like this. This entire protocol is currently put up in 4 different phases. The first phase is qubit B and C are prepared. We require probably maybe an entangled photonic devices or entangled photonic sources, and somehow we create these two entangled particles, right? So they could be two photons. One is held with Alice, other one is held with Bob, right? And what we typically try to do is we just distribute them over a quantum channel, right? So Alice and Bob have each one of them, and we ensure the fact that there is a measurement that happens at Alice end. So what does Alice do? Alice typically does what is called the Bell state measurement. And Bell state measurement is a measurement where we typically take two qubits, combine them together, and then identify what exactly is the so-called Bell state. Bell state typically could be in any one of the 4 states that originate because of this Bell state measurement. So what does Alice do? Alice does a Bell state measurement with respect to A, the qubit that needs to be sent, and B, the qubit that she has got. And the moment that happens, the entire state collapses, right? The moment you do a measurement, quantum theory says that it collapses. And the moment it collapses, instantaneously at the other end, at Bob, also the qubit held with C typically also sort of collapses, and then it takes over to the original state of A. So that is how I'm able to achieve a teleportation of the state A from Alice side getting onto the Bob side, right? And how does the Bob get this? Typically, Bob gets this by doing some sort of a unitary operations which he applies on the data he receives from Alice. So Alice sends these two classical bits to Bob on a conventional channel, not the quantum channel. Okay. So because of this, Bob typically can extract the original state of B. So here we say that I'm essentially having a communication mechanism, a protocol that is put up in place, wherein entangled particles are typically used to ensure the fact that qubits are transferred. Typically, when I say transferred, the state is actually transferred from Alice side to the Bob side. Okay, we are going to use this concept in a little more in detail when we look at a few of the protocols. So that is the reason why I'm spending a bit of an extra minute out over here. Next slide, Prakash. So when you look at teleportation, teleportation also plays a very significant role in QKD. Right. So what is the typical role it plays in QKD? I can use this concept in quantum repeaters, and by doing so, I extend the range of this QKD infrastructure over longer distances. As Nikhil and Vipin had spoken earlier, normally get at this particular point of time some sort of distances. Let's say you talk about fiber optic, and fiber optic has its own issues in the context of a tolerable type of an attenuation that needs to be somehow handled. You can reach up to 80 kilometers, 100 or maybe 125 kilometers, and beyond that you definitely require some form of a repeater. And that repeaters have to be quantum repeaters, and teleportation gives you a very good opportunity to sort of implement them. And how do you do that? You use a technique called as entanglement swapping. Okay, so next slide, please. So what is this entanglement swapping? Just assume that you have got two pairs, right? Let us call this pairs as let's say two entities. Let us say that each of them have got two pairs of particles. I call them as A and B. Similarly, at the other end, you have got two pairs, typically called as C and D. And when we have them just like that, they are typically in a balanced state. Like you see, Alice is having two pairs here, the bell pair, and the Bob is also having two bell pairs marked as the reds and the blues. Now, what we do is we perform what is called the bell state measurement. And how do we do that? We bring in Christine as an intermediate person, as an intermediate resource, and then manage the so-called entanglement through a bell set. So I extend this concept of entanglement. I'm just doing an extension. So how do I typically do that? We will perform a bell state between these 2 points out over here. Okay, I cannot just move that. Just imagine, yeah, correct, Prakash, thank you so much. So we just perform an entanglement between, let us say, particle B and particle C. Particle B is from Alice side, particle C is from Bob's side. And that is typically what is given as a role and responsibility to Christine. And by doing so, what happens? These two particles typically now collapse. And that creates a new entanglement between A, the first particle, and D, the last particle. A is with Alice and D is with Bob. So this is what is called as entanglement swapping, and this entanglement swapping goes in a long way in terms of setting up a sort of a relay of a network. So we are sort of relaying the quantum states. Next slide, please. Okay, so when you look at the transmissions that are typically possible or what are normally used out over here, you have two basic ways. One is a direct mechanism and other one is with teleportation. So this also gives you two approaches. One is a direct approach for a QKD, other one is a teleportation based approach with QKD. And I think this is a pretty very straightforward to understand the fact that the direct approach do not need to actually use the entanglement phase, whereas the teleportation based QKD will have to use a let's say an entanglement out there. The entanglement is very much required. And when you talk about a direct QKD, it is more uh, on a sort of a conventional type of an approach. We normally have a distance limitation, and the distance limitation is all because of the channel noise and interferences and all the errors which typically creep in out over there. Whereas the moment we talk about teleportation based QKD, right, the distance limitation is much lower. So the limitation is not there. So you can probably extend it down. And we can also use this concept of a repeater, which I just now told you. And using that, you can extend this distance much further. Research is typically going on. Let us see, probably in the next 1 or 2 years, we will see a lot of additional news coming up there. But the fundamental difference between these two happens to be something like this. If you talk about direct QKD, it works on a single photon type of a source. Whereas the moment you talk about teleportation based QKD, it will work out on an entangled pair of photons. So that is something very important to understand. And the moment you talk about teleportation based QKD, the equipment costs are a little different. They are higher. You require entangled photon sources, Bell measurement stations, and all of these are a little more expensive in terms of your implementation. Next slide, Prakash. These are a list of a few of the real world implementations. I think also Vipin had spoken about that. Very quickly, I'll just summarize them. China has a project which is a satellite based QKD, which is connected some parts of China to Europe, and primarily they wanted to demonstrate teleportation, and they could achieve this over a typical range of about 1400 kilometers via satellite. Then IBM, Google, they are in constant endeavor through their academic labs, and they are also exploring teleportation based QKD. The Swiss Quantum Network and the University of Geneva is establishing a metropolitan area QKD, primarily wanted to interconnect all the institutions, the research institutions in Geneva, and they already have an existing fiber backbone, so they are trying to piggyback on top of that, and then they're setting up this metropolitan QKD. Tokyo has come up with once again, along with participation from NICT, Toshiba, and other companies, they have set up a Tokyo QKD, as they call it, and it's once again a multi-node QKD spawning across the city of Tokyo. And their objective was primarily to check out and validate different protocols, and just wanted to identify what exactly is the interoperability level across all these QKD protocols. And SK Telecom from South Korea had set up already a commercial infrastructure, once again based out on the 5G infrastructure. So I think Vipin might throw additional light on this. He's a 5G expert. Back in the US, you have got Quantum Exchange, and they have set up a QKD backbone connecting New York and Washington, D.C. And what they are planning to do is they are offering QKD as a service, right? It's a SaaS type of solution where QKD is being offered, and they have exposed this to the government sector and the financial sector. India also has got its own role to play, and there are a lot of things that are happening from IIT Delhi, and I think IIT Madras and CDAC and all those institutions are going in a very big way, and we have seen some implementations of ISRO through their small satellite network, and all those things are happening in India. We are just waiting for the big bang to happen, probably by the year 2026, sometime in June, July. We are waiting for some announcements. Next slide, please. So what we will now go through is a very quick run through about this QKD protocols. Okay, next slide. So when you talk about QKD, the QKD essentially follows a small pipeline of an activity. Okay, so whenever you want to implement a QKD, we follow this sort of a pipeline of an activity. So let me just tell you about this pipeline of the activities previously. Yeah. But first, it starts off with the activity of state preparation that happens at the Alice side. So Alice will have to do some sort of an encoding. So Alice will use some basis states, and using that, Alice will do some encoding. So that's the first step. Then goes into transmission. Right. So Alice sends out this encoded quantum states to Bob over a quantum channel. So that is second phase. The third phase is where Bob will do some measurements, and Bob will do some measurements using some randomly chosen basis. And the idea is, how do I get a secret key? The secret key is typically generated by some sort of a random behavior that happens both at Alice side as well as the Bob side. Right? So Alice generates maybe a bunch of what do you call states which are randomly generated, and they are transmitted over a normal channel. For Bob also will typically generate a series of random states, and using that random key states, he will also check out, and then they will both compare whether there is any match that is likely to happen. And thankfully, because of this quantum superposition as the driving factor, we expect maybe a 50% of a chance of a match to happen. So using the concept, a raw key generation takes place. Right. So raw key generation is more or less good enough, but we want to now clean it up. If at all there are some errors which are identified, the errors needed to be recovered out, and for that we carry out a series of post-processing, and post-processing is normally done in the conventional domain and primarily used for correcting any errors which could have crept in, or if there is any eavesdrop who has come in, we want to detect that and then identify what exactly is the impact of this eavesdropper, and if required, we might even discard this entire key that has been expired. So quickly, this post-processing is also very, very important activity within the pipeline. So the post-processing is once again spread over 5 different phases, and the phases are more or less the same, but the method that you employ could be different depending upon the protocol which you are using. Okay. So what exactly are the post-processing activities? The first one is what we call it as a shifting of an operation. Shifting operation is basically, let's say you start off with thinking about a 24-bit, let's say, a key, right? So that 24-bit key is what is randomly generated, not exactly the key per se, not exactly the key values per se. The key values are generated, and then Alice will also use random set of states or the basis states to manipulate them, to model them, and that's how information is sent out. Right. So what happens is, at the receiving end, Bob will do some sort of a matching, and depending upon how many bits are matching, they will get only a partial key generated, and that particular partial key is the sort of a shifting of an operation. So shifting operation is trying to remove all the bits which are really not concurring with each other, and trying to ultimately get out a small subset or a partial key. Okay, so partial key, it identifies all those places where the bases which they have chosen have a match. After that, we also try to identify the quantum bit error rate, the QBER. Now, how do we identify the QBER? If there is a perfect match, 100% match, that means what, the error is not there. But normally that does not happen, simply because there will always be some form of an error that is introduced, either because of the channel, or because of some noise in the detector, or because of some guy who is trying to poke into this entire communication. Right? The eavesdropper is there, Eve is there. So we would like to do an estimation of the error, and for that we just pull out a small subset of whatever we have received, not all of them, So we just pull out maybe a small fragment of that and then try to find out of this small fragment which you have selected out, how many error bits are there. And we estimate the QBER, and there is a small mechanism that sets up saying the fact that if the QBER is less than 5%, then the channel is clean enough. A QBR between 5% to 11% indicates the fact that the channel is a little noisy, but still okay, it is acceptable.
Something holding, just a sec. Are you able to see it only? Let me
No.
probably stop sharing and reshare. Yeah, just a second. Let me reshare. Let me just share. Yeah, okay. I think it should work now. Sorry for that. Yeah, I think I had to do a slideshow. Yeah. So while I was moving,
Yeah,
I think it, yeah, go ahead.
Yeah, thank you. Yeah. Okay, so that is where we check out, and the standard is something like this. QBR between 5% to 11% is supposed to be indicative of a noisy communication. Then we will use some other methods to correct the errors. So that is about error reconciliation. And if this QBR is more than 11%, it is indicative of the fact that there is an enormous amount of noise which is not even worth enough to recover from this particular noisy channel. So we normally dump it off. It also could be because of the fact that there is an eavesdropper. Eavesdropper has come in, and then some sort of a deviation, some sort of an error that got introduced because of the eavesdropper also is resulting into a QBR greater than 11%. Okay, so then the third phase is error reconciliation, and we typically try to identify what are all the small mismatches which have occurred and then try to correct them. So the mechanism is not error detection, but it is error correction as a mechanism, and we will have Dr. Radhika Madam to give us a complete overview of this error reconciliation mechanisms. Having done that, now we have to have a mechanism to convert this key rather than sharing the key. Sometimes the key could be pretty long enough. We would like to hash it and then convert into a hash mode. So we have a hash function implemented. The hash function is done through a tuplets matrix. This is a let's say n by n matrix where all the diagonal streaming elements are the same elements, and that is a very nice hash function that is typically used. It is also called the universal hash function. So that hash function is what is applied on that particular derived, let's say, key. And once you have the hash function that is available, then that can be typically distributed on your conventional channel itself. So that generates the final secret. And if at all you want to add up a additional sort of a key verification mechanism, you can just bring in your normal techniques of, let us say, putting a hash digest onto that, signature verifications, all of that can be added to ensure the fact that message delivery is done in a proper way. So once the key is available, the shared key is available, then you use your regular standard encryption mechanism like AES. So that happens in the classical communication system. Move forward, Prakash. There are a few challenges. I'll not get into the core details of all these challenges, but these challenges are sometimes more specifically driven out of the physical properties of the quantum mechanism and the underlying hardware. So you have to face transmission losses. You have to face some issues that come up with the detector side. More specifically, the detector cannot completely and comprehensively detect a single photon that is coming from the source. Other thing is all about the QBER, which I currently spoke to you. That is also very important aspect. You need to be always sensitive about the QBER because that is one type of a tipping parameter which tells you whether you're going to accept the communication or reject the communication. Then you have got side channel attacks. The side channel attacks come in because of a whole series of issues in terms of how you time synchronize them, in terms of, let us say, the variations in the power. People are there who observe what exactly is the heating patterns across all your electronic devices. From there, they try to identify what exactly is nature of information that is flowing and so on and so forth. So these are basically what we call as a leaking mechanism of information. We are not actually getting into the actual data. Actual data is not being touched upon, but by observing all the other paraphernalia around this quantum infrastructure, people try to attack and then try to barge in. You also have to handle issues with respect to what exactly is the maximum size of a key which you can handle. Bigger the better, as people say, but at the same time, how much big? Because the moment you talk about big keys, you also require that sort of a infrastructure that you need to use to perform all these operations as well. The sixth issue, which is also very much that needs to be addressed, is the way you go to integrate this with the classical infrastructure. Remember, when you talk about QKD, the quantum resources are not typically used for compute intensive operations. We are not doing that. We are using the quantum infrastructure primarily to exploit its other type of phenomena like superposition, entanglement, and teleportation. We are primarily banking on these properties of the quantum phenomena, not the so-called phenomena of extreme compute power, which I can also derive from there. So, right. So ultimately, we need to come up with mechanisms where QKD can also coexist with existing networking infrastructure. And scalability costs is another issue that also needs to be worried about. Next slide. There are some vulnerabilities in QKD. We need to also just have a general idea. I'm not going to expand on this, but the most important vulnerability, typically what people talk about, is the PNS attack. The PNS attack is also what we call it as a photon splitting attack. What exactly we mean by the photon splitting attack is this. We normally assume that there is a single photon that comes out from a source, but sources are not absolutely ideal, so they might be generating multiple photons in a small time frame. And what can happen is the attacker may split this photon stream, and then he can coolly sort of store one, steal one, sneak one, and then store it in what we call it as a quantum memory. And once he stores it into a quantum memory, probably he can use this later during the reconciliation phase. So if at all he gets access and he can probably guess this out, he's getting typically some partial information upon which he can cook up and then typically work on this. So this is something which is a possibility. And the way we counter this is using what we call as a decoy state protocol. And instead of actually sending the base states, we also send some sort of a false state, the decoy states, and we put this sort of an attacker into a small trapping mode. He just goes on to capturing the decoy states, and from there we can identify whether the attacker is there or not. Okay, so that's how we sort of put up a bait and then try to check out if the attacker is there, sensing our information exchange. Then you have got Trojan horse attacks and detector blinding attacks and time shift attacks. All of them are additional type of an attack which we need to be aware of. These are the ones which offer the so-called vulnerabilities. Okay. Next slide, Prakash. So let us now quickly get on to a brief taxonomy of QKD protocols. QKD protocols are studied and they are categorized as follows. We talk about prepare and measure protocols, and these are the protocols which work out on the core basic premise, wherein someone prepares the system and someone measures the system. Something like Alice, as one party, prepares the quantum state, sends them over a channel, typically the quantum channel, and Bob receives them and measures them. As simple as that. And you have got a whole array of the protocols which are available, like BB87, one of the oldest one, and that is also very, very popular and often widely used. Then you have got B92. B92 is a small modification of the BB84. We will also probably, if time permits, touch upon that. BB84 uses 4 polarization states, whereas 92 uses just half of them. It uses only 2 orthogonal states. Then you have got SARG, that's basically another protocol which uses or encodes bits in non-orthogonal states, and it does it in state pairs. Okay. Then you have got the decoy state. This is a very important type of a protocol. We are going to discuss about that when we talk about the cow protocol. Next slide. There are some protocols which are purely based on entanglement, and these protocols effectively rely on quantum entanglement. Okay, so the idea is, I think, pretty very simple. There will have to be a mechanism by which Bob and Alice will have to share a pair of entanglement. So for that, we normally have a third party entity. Either the third party entity is measuring them simultaneously, or the third party entity is just sourcing the entangled components. So you have got once again protocols which are E91 protocol, BVM 92, and DIQKD, the device independent QKD protocol. Okay, so these are the 3 protocols which fall under the category of entanglement based protocol. You have got MDI, the measurement device independent. It's not just only device independent, it's now talking about measurement device. So it's not DI-QKD, it's MDI-QKD. And the typically idea is Alice and Bob, they send quantum states to a third party. Charlie is the one who does the Bell state measurement. And the results of the measurements are actually announced to both of them over a conventional channel. And this is okay even if Charlie is taking that particular third party's role, or it could be even the eavesdropper Eve taking the third party role. Okay, so this typically works in all scenarios simply because of the fact that only the quantum state mechanism is what is handled by the third party. The actual data bits and the key bits are not typically known. Okay, so this is popularly used in MDI QKD. Next slide, Prakash. We have got continuous variable protocols, and these continuous variable protocols use not the discrete representation, but they use the so-called continuous spectrum representations, where the entire encoding happens to be in the form of amplitude and phase of the so-called coherent light pulse. So you have got the Q and I, the quadrature representation of both the phase as well as the amplitude. So both of them are now used to do the encoding. And the way this is done is to ensure the fact that like the way you have it in your regular normal, let's say, radio communication, you also sort of modulate it and then throw it open into the open air, and then you have a receiver which is a heterodyne receiver. Then heterodyne receiver will have a tuner tuned to a specific frequency, and then you selectively pick up that particular transmission of a channel. Quite similarly, out over here also, you have a mechanism wherein you ensure the fact that whatever is the encoding that is being done, it is sticking on to the Gaussian representation. By Gaussian representation, we mean the fact that most of the information that is sent out is very, very close to the mean of the signal. Very, very close to the mean of the signal. So that's the very most popular type of an encoding. And this sort of an encoding is also very well known and understood, and is rampantly used in most of the current communication technologies also. Next slide, Prakash. Okay, so this is a quick example of how BB84 goes in. I just only go through this BB84 because of paucity of time. I think I will move fast, and then let me just get on directly towards the end. There are some other protocols which are listed here. You can very quickly go through them. So what we have got in BB84 is something like this. This was introduced by Bennett and Bassard in the year 1984, primarily even before this quantum computing as a field really was thought. And his idea was to ensure the fact that, okay, using this behavior of quantum mechanics, if at all that can be brought in, he can come up with a encoding scenario which gives him an opportunity to have the key distribution that can be done for symmetric key environment. Okay, symmetric key now become very much in the limelight simply because of the fact that people now look at the quantum machines as a threat to break into asymmetric type of keys. So that is the reason why symmetric keys are very popular. But you know, you have got a lot of headaches about handling symmetric key because of the key distribution challenges. So what BB84 does is something like this. We use typically two type of bases. One base is called the rectilinear base, that is the 0 degree, 90 degree type of a polarization. And the other one is a diagonal base. And the diagonal base is the so-called diagonal polarization 45 degrees and 135 degrees. So if at all I'm using rectilinear type of encoding, I have got 0 that is encoded along maybe the up and down, right? And 1 is encoded along the sideways, right? Similarly, if at all I've got diagonal polarization, which I look at, and this is very much possible using the so-called photonic type of single photon sources. It can be very easily done using the polarization hardware. And I once again polarize for a 0 along 45 degrees and 1 along the 135 degrees. Right? This is a typical standard which is understood and accepted both by Bob as well as Alice. So what now happens is something like this. Alice will have some sort of a key. Alice picks up some sort of a key, an arbitrary type of a key. Randomly, she selects a key which is made up of zeros and ones. If they decide that, okay, the key should be, let's say, 40 bits, then she will have a stream of 40 bits of zeros and ones. Right, here is a small example. We have got a bunch of transmitted bits. That is a bit that need to be transmitted. And what she does is, now she arbitrarily, randomly, once again picks up transmission bases. So these are the bases. And because of these bases, right, what she now will do is she'll represent using these sort of bases that she has selected. Remember, she's not selecting one basis for all. For each and every bit that she wants to transmit, she will select either the rectilinear base or the diagonal base. And accordingly encodes this 0 or a 1 in that particular base. So you have got these things which are now ultimately transmitted. These are the pulses which are actually transmitted using a single photon source. What happens at the receiving end? Bob will start measuring, and to measure that, he really does not know how to measure them. So he will once again randomly choose some bases. So he will randomly choose some bases, and then he will start measuring them. And once he has measured them, he will now store also a bunch of received bits. Remember, these received bits might not be conforming to the transmitted bits. So, but to identify whether he has received them correctly or not, Bob does not actually transmit these received bits. He will just keep them with him. What he will do is he will just only transmit back the measurement basis. Okay, so this measurement basis is what is exchanged, and what they now do is they'll just compare whether the measurement bases are matching or not. So whichever places the measurement basis is matching, here and here and here and here and here, typically they take out the data values. This will be the derived key. So just notice the fact that now the derived key is more or less 50% of the bits from the starting point. The starting point was this number of bits, and now the derived keys may be about 50% of the bits which are there. And if at all the EV is not there, obviously now this forms what we call it as the shared key. Next slide, Prakash. Okay, here is a small example of what we now need to do with respect to the post-processing. So let us directly get on to the error estimation, which I spoke to you earlier on. Then if at all there is no eavesdropping, nothing happens, then the QBR will be definitely less than 5%. If the channel itself is having some noise, if the detectors and the sources are having some noise, then obviously it might be a shade higher than this, but definitely it will be less than maybe the 11% depicting a noisy channel. But on the other hand, if there is a Eve that is coming into picture, what Eve will try to do is Eve will try to maybe add up some of its own bits. Right, he will introduce his own bits. So some of the bits coming from Alice side, he'll grab it off, and then he will try to put in something else. Because of which, what will happen? The matching does not happen at all, and the mismatch rates will be much more higher, because of which the QBER will be in excess of 11%, and that indicates the fact that there is some sort of an infringement of privacy, and we feel that the security is compromised, and then we completely knock it off. While if there are some errors that are happening, right, there is no infringement that is happening, but there are some errors. There could be some detected errors and stuff like that. Then we get out to this error correction mechanism. So that error correction mechanism is through LDPC or some cascade protocols, and that will once again have your entire key recovered out from the errors. And as I told you also, once again we use a hash function, and that particular hash function will generate a hash digest for whatever is the key which we have generated, the shared key which we have generated. So next slide, Prakash. So what do we need as a hardware? So from a fiber optic channel implementation, we require a single photon source. We require some polarization filters. We also require photon detectors. And in case you are using some entanglement as a mechanism, then you also require entangled photons. Now, entangled photon sources are reasonably more expensive compared to the single photon source. I'm not a complete comprehensive expert on this particular photonics as an area, but my gyan is what is given by information which I've collected online. Okay, and as we also know the fact that previous slide, Prakash. Yeah, as we also know from the general fact that most of the equipment will have their inherent background noise, and that is the reason why you have to ensure the fact that there has to be some sort of a error correction that has to be implemented. So you can always expect some QBR. QBR can never be equal to. Yeah, Prakash, next slide. So this, I'm not going to the details, but this is a E91 protocol which is going to use entanglement. So the concept is something like this. There is a common entangled quantum source. And what that entangled quantum source does is it typically generates an entangled pair of particles or photons, and then it distributes that to Bob and Alice, one each. Bob and Alice will pick up, let's say, some bases. For example, the base could be 0, pi by 8, pi by 4, picked by Alice, or minus pi by 8, 0, pi by 8 by Bob. And using this randomly out of this set of bases, it will start encoding. And after that, the entire concept is once again the same scenario. So we just have a normal public channel over which the bases that have been selected are exchanged, and wherever the bases are matching, you normally get a small differential. And what we have is we split up whatever is this matching part and the non-matching part into two. We keep the matching part separate. The non-matching part is what we essentially pull out to find out what is the way, whether there is any infringement that has happened or not. And for that, we use what is called the bell test that we perform on that non-matching part. And if the bell test fails, then automatically it means the fact that there has been some sort of an eavesdropping that has happened. We just discard whatever we do, and then we go in for a retry mechanism. Next slide, Prakash. B92 protocol is a simplified version of BB84. BB84 uses 4 states, whereas B92 uses only 2 states. For example, Alice uses the polarization states of 0 degrees, 45 degrees. Once again, they are not orthogonal, so these are non-orthogonal states, whereas BB84 uses orthogonal states. Similarly, Bob also uses 2 states, which is, here it is an example like minus 45 and 90 degrees. These are 2 non-orthogonal states, and the rest of the thing is once again the same, absolutely similar to BB84. Next slide, Prakash. This is a decoy state protocol. The decoy state is something like this. We also call this as a coherent one-way protocol or a cow protocol. Right? It's also an enhancement of the BB84, but uses a small technique of introducing some additional pulses, and these pulses are called the decoy pulses. So what is done is, whenever you are typically transmitting these pulses, you are typically going to transmit in small time windows, and in each of the window, you normally generate a pulse, which is a pair of values which you are sending out. And these pair of values are not the physical values, but these are like 2 pulses of 2 different amplitudes. one with a very small amplitude, that particular pulse is called as a vacuum pulse, and we have a normal pulse of a regular amplitude. So these are the two amplitude pulses which are normally sent out. So what is the way we send out? To send out a 0, that is encoded as a vacuum pulse, that is a pulse with a very small amplitude, followed by a non-empty pulse, that's an actual full-blown light pulse. And a 1 is sent out in the opposite way. For a 1, we encode it as a non-empty light pulse and plus a vacuum pulse. So this is a sequence of two pulses which are sent out. Then you try to lay a trap for an eavesdropper. And to lay a trap for the eavesdropper, previous slide, Prakash, 1 second. Yeah. So what you do is you define what are called as the decoy states. And the decoy state is defined as a series of two non-empty states or a series of two empty states. Next slide. Okay, so this is how it happens. Alice is the one, there will be the intensity modulator which is coming out from a laser source, and that sends out this sort of a pulse. You just say the blue pulse is an actual pulse and the white pulse is an empty pulse. So this is how normally we try to send it out, and the bit values will be either 0, 1 or the decoy state 0 or decoy state 1. So you have this sort of a transmission that is done. And what does Bob do? Bob uses what is called an interferometer. I really do not know much about that, but I know the fact that this interferometer has a bunch of detectors, right? One detector typically directly smoothens it out and takes the data line that is sort of sucked out, and the other part is typically given out through two detectors, and these two detectors essentially are meant to identify the state. So these are called the monitoring detectors. So there are two monitoring detectors which are put in. One is directly coming in phase, other one is slightly delayed by 1 bit. So it's something like an out of phase. So what you receive here is just nothing but a series of these pulses slightly shifted by 1 bit delay. So you just process both these two to identify what exactly is the level of a coherence, and from this level of a coherence you will identify whether there is some eavesdropping that has happened or not. And all of this is once again handled through let's say post-processing procedures. So here the idea is you are looking at the coherency between these sort of pulses. Next slide, Prakash. I think I'll skip on this. We'll just go almost to the last slide. I'm running out of time. Yeah, go to the last slide also. Almost to the last. Yeah. This is a quick comparison matrix. You can just look at it. This shows up a series of these protocols and what type of a level of a security it offers. What are the core features, and it also exposes the sort of a vulnerabilities for the type of an attack that these protocols are subjected to. Right, they are susceptible to, let's say, BB84 is susceptible to the PNS attack, and E91 has its own way by which it has to ensure the fact that entanglement of the sources is very much as a criteria that is required, and measurement devices have to be trusted, and so on and so forth. So all of that is listed out in a very simple comparison matrix. For those of you who are interested, you can spend a few additional minutes to get some information about that. So this is in summary. The MDI QKD and the DI QKD offer the strongest theoretical security, and they are good for side channel attacks. Decoy state BB84, once again widely deployed in the real world, especially in the fiber world, because it typically can very easily detect eavesdropping. E91 entanglement based protocols are primarily the ones which are traditionally used for quantum networking, most specifically based out on the teleportation concepts. And BB84 still happens to be one of the very, very popular and most commonly used, sort of a low-hanging type of a protocol, easy to implement, and it gives you reasonably good enough result. CVQKD is essentially showing a lot of promise, especially because it has got an opportunity to play alongside the radio wave architecture supported from the telecom infrastructure, telecom supports. So that is all I have got. Thank you, Prakash.
Yeah,
For,
thank you, Gokhale. Though a little extended, it was really very attractive for people to understand the concepts. We'll move on. I'm taking the next one. The focus of my and thanks. We'll take the questions at the end. Gokhale and Vipin and Nikhil. I'll move on to fiber channel. So we call it FC. So fiber channel, I will go through some of the key issues and I'll do it rapidly because we have shortage of time. So myself, I have a background. I am from IIT Bombay and have been in the industry for 30 plus years. And most of you know background. So I'm a IT guy with 5G as well as quantum. I'll leave it that with some semiconductors. So more electrical engineer. Now coming to fiber channel. Fiber channel has standard topology and this is theory. If you look at what Nikhil said that they've got P2P and P2 multi-point and all that, these are represented through three of the standard approaches. And since I am going at the fiber level, which is at layer 2, media is the fiber and the channel is allowing the frames at layer 2 to be transmitted. They call it as packet data unit. So when you have a fiber channel, there are FCP2P, arbitration loop. Here you have got a direct point to point, and here arbitration loop means this is like a ring. You can have a ring like your token exchange, you do something like that, but more of a ring. You can have one ring, two ring, so make it redundant types. And the third one is the fabric. So each of them are named as something depending on what nodes they are. So the concept of node is important. When you have a node, we call it as node itself has a name but does not in itself do anything. All things are always managed by the ports. So that is why you look in fiber channel, the port density, higher the port density, higher the capacity. You can see here number of ports point to point is only 2, so there are only 2 ports. So node name 1, node name 2 talking to each other. The total address is 64. So total name ID is 64 bit, out of which only 24 bits, which is you can say hexagonal FFFE example. This is the login address. So you have to log in into from the port name. You have to attach to the ports, and then ports can talk to other ports. So it is always, if you are doing direct, then it is n port to n port talk. If it is arbitration loop, then you are going from one to another until you find what port you are working on, and then they will get attached. So attach detach is important in arbitration loop. That is why if there is a failure, then you have to release yourself and reattach to another one. So that is in the ring topology. You can go counterclockwise, clockwise if you have a availability of survivability. But in the case of switch, it's everybody only talks to the switch. So switch itself is the fabric, and that contains all the information required to connect to it, and therefore the capacity of switch is higher. In the case of point to point only, it is number of ports is 2, so divide by 2, so only one bandwidth is there. Whereas in case of 127, you can do, but they are fixed. Like everybody is a 10 gigabit, you cannot have then 100 gigabit in that. So arbitration loop has a standard. Whereas in the case of switch port, the Ethernet switch which is there, not the Ethernet, sorry, the optical switch is there. That is the one which, if it can go up to 2 to the power 24, that means over the globe you can have world network with 2 to the power 24 nodes. But actually divide by 2 is the bandwidth, and everybody gets a login to the fabric and detaches themselves when they have acquired whatever they wanted to get the link, and then transmit to each other. So transmit, receive, these are, so there are many concepts in this. If you have only one fabric, you can only have or 24. Now what happens if I have two fabric switches? Then I extend it. So there is a extension called E. So there are interfaces which are defined differently, E port, B port. B is for bridging. So bridging means if I want this to be connecting to LAN, WAN, MAN, etc., then I'll do switch to the B port will be there. So there are different ports defined, and each port is able to deliver what you need to be able to achieve overall in the fabric in the layer 2, which is all there is load of information you can get from open shortest path first and OSPF onwards to many. But essentially this is the fiber channel technology. It does not have equivalents of IP, but they have tried to manage to bring it like IP, but not necessarily IP. So you can see that you can have fiber channel over many yeah. So you can do it under SCSI for storage. You can do fiber channel over Ethernet. You can do over ATM. You can do over SONET. The packet data unit differ for each of them. You can do an IP for internet. So that is the MAN, WAN, SAN, and all that. Whatever is there, you can connect. So the communication can be synchronous, asynchronous. They are all based on the request, response, and unsolicited three commands that are available, and these commands are available through common transport protocol called FCCT. So you do through FCCT, fiber channel, request response, unsolicited message, etc. And these are all based on the previously 802.10, IEEE 802.10 fixed, which is one. And then you got 1Q, which is for the wireless, or for the fixed wireless combination, and that got into 802.11i, which became for the Wi-Fi, and then WPA2, and then you got space and non. So there are various IEEE standards which have been adopted over years, and it has become very strong in the sense. But only thing is the capacity is what matters at this time. And most of the internet today use 10 gigabit to 25 gigabit. So most of the optical goes in 10 to 25, and they are called pluggable SFP connectors which they use. And when you go into 100, then it will be SFP. So QSFP. So standards, of course, there are a lot of what you call NZ, zero, non-return to zero, and return to zero, and then PAM, and that is power. So there are many protocols, but standardization is key, and it's driven by the various industry bodies and MOPE and all that. So just state that class of service is the key to this. So if you find a fiber, you will have an N1, N2, which is nothing but the core and the clad. So when under the core, and this core, the clad over the core has a density, so that you are able to do internal reflection. Snell's law physics, normal physics is you got Snell's law, where if you have a density, higher the density, you are able to deflect. So if you do internal reflection of the laser or the photon, then you are able to contain that, and that is what the key. And there is a quality associated with it. There are class of service, they call it, and there are class of service 1, 2, 3, 4, 6, and F. F is for the fiber, which is fabric itself has some exchanges, and it can be one PDU, and it can work across with 1, 2, 3, 4, and 6, so that they can do the supervisor request response and or error and all that. So 1 and 4 are the ones which are guaranteed. So you know that P2P is always going to be 1, because you know it, 1 or 4 are depends on. That's why there is a table which I showed you. You can look at it, that what are the various things are allowed, like class 1, 2, 3 you can do with P2P. Class 1, 2, 3 you can do with arbitration loop, and 1, 2, 3, 4, and 6 can be done with switch. So switch fabric is the only one where you can have 4 and 6. But I'll come to what 4 and 6 are important, because for us we are talking about virtual MFC, that is multi-fiber. So if you have one channel, one line like this, and then in that you want to do 4 virtual, that is what the are 4 virtual, because we wanted to do 4 waves or 4 colors within the same channel. So that is why that is virtual. So 1 and 4 are guaranteed. That means there is guarantee of return, and there is sync and asynchronous. So second is like connectionless, but connectionless with acknowledge ACNAC. That means you will be guaranteed that you have the request and response to ensure that you already have know that you send that in order. If it is in out of order, then that may be possible, but then there is a confirmation for that. Whereas third is like your datagram services, like your UDP types, where you just send unacknowledged data. You keep sending, you can flood it and you don't know what happened, but that's the way. That is simpler one, but does not satisfy the guaranteed requirement. Fourth is the one which is connected, where you have got a flow control. Is a virtual channel ready or not ready, like we do RTS, CTS in our serial interfaces, something similar. There is a virtual circuit. So 4 is the most important for 6 is for SAN, which is for storage area network. We'll skip that. So from our point of view, the important thing, key exchange. And the key, when you want to exchange, then you have to have two nodes, node port 1 and node port 2. We can see there are two. They want to communicate. And Charlie, like Gokhale mentioned, there is a Charlie. So our key distribution server is Charlie in this case, where they go, both of them exchange their request. Hey, this is my key request, and this is nothing but running on a port which is called FFFF7, which is the key exchange port over which the security negotiation occur. And you send a request, and the key exchange server, it's like a ETC services and ETC protocol like we do in the IP era. Layer 3, similar, this is at layer 2, where you got the FFF7 port over which you poll. So node 1 and node 2 both will get attached. By getting a request, they will get the key, and then because this is a key distribution service, once they have got the keys confirmed, they can accept the response, and then they can, both of them can start the secured communication. And so you remember that in the PQC we said that there is a MLKEM encryption ID, which is what we have to do. So there is a size, our size is 512, and MLKEM is our key. So there is a field which contains when you send that, hey, this is what I want to get done with this key, and this is what my exchange information, and this is my, it can be a hash key or it can be MLKEM, in this case for symmetric key exchange, as Vipin, Gokhale, all of them pointed that it is the symmetric key which is important, and this is what is done through this key type. And once you put the key type, and they call it SAID or something, that is secure additional information delivery, and that whatever that additional attribute is there, that is used to pass this information and accordingly get the QKD over fiber channel. Now QKD does not have to be over fiber channel. Fiber channel is for the optical only, but if you are going to do over the free space optics, which is nothing but, when we say free space optics, we are referring to non-terrestrial. Terrestrial is, we know that it can be in the troposphere up to the limits of the atmospheric, and then beyond that. So 300 kilometer range and 900 kilometer range are the ranges for the, at least the upper limit for this one is 900, and lower limit for so there is called LEO and GEO. LEO, MEO, GEO. LEO is the low Earth orbit, which is up to 300 kilometer, and beyond that up to 900. Above 900 is all for the MEO, and this is for the 36,000 feet kilometers. So you got the coverage depends on the radius. So if you have got a 300 kilometer, your radius, if you do arc here, it will only be 300 kilometers. So it can coverage up to 300 kilometers. Normally you will find that free space optics allows you a certain limitation, and there is a power limitation. To give you a sample, if I say I have a 0.8 dB per kilometer, I am going to lose attenuation. So if I have 1000 kilometer, I will get 180 dB loss. 180 dB loss is equal to what? 30 dB is around 10 to the power 3, and it is minus 3 because we are talking of power going down. So 10 to the minus 3, and if you multiply by 630 into 6, 180, so 10 to the power minus 18. So if you are going to get a loss of signal of 10 to the power minus 18, how do you really recover it? There is a limit on how much you can recover based on the signal strength. So your amplifiers and all that should be good enough to do that. So depending on whatever those numbers are, we just say that if you have a satellite which is moving, and then that has got classical connection as well as quantum connection to the ground station A and B. Then whatever they transmit, we prefer a down link. There are other configuration, but downlink is easier to do. So therefore, our Charlie in the air in this case is not the key. The key exchange server will be running in the satellite. So this is same satellite at position A and B, with a station A and B getting their part of the key exchange, and that is how the establishment is done. And thereby we are able to recover the A and B at the station by using the either you call it as tensor or exclusive OR. Simplest is exclusive OR, but you can do a tensor of Ka, Kb, and then you can use, because both of them, only Charlie knows. Charlie means our satellite knows there is a trusted party which is able to give you both A and B, and each of them, when their turn comes, they access, because you are not going to get 100% all the time. It goes around, and whenever you get your access to the window of opportunity, you get your key exchange and then establish the key, and then you can use the ground channel, because key is what is done over the satellite satcom, whereas the station themselves are connected indirectly. So only key distribution is done through the satellite. So this is how it works, and there are many options, like you can do a downlink only, uplink only, downlink with various combination, having one satellite with two connection, one downlink, uplink, reflector, and then have two reflectors, and do the inter-satellite link at the top with two satellites. So there are many combinations. That is called hybrid, and hybrid QKD can be done with MEO at the top, LEO in between, and at the bottom we have got the various stations. So these are the various space-related key distribution mechanism. So my summary with this is that you can do D2S is the new satellite. That is, you can have a device directly talk to each other. So it's called direct to D2D. So D2S and D2D are the ones which are new things you will hear from the SpaceX and all those. And this is important. So optics and free space optics both are important, and they are really based on optical principle, but they have their own way of managing the attenuation bands and all that. So I'll leave that. With that, I'll pass on the last part to QAD error correction, which is related to CSS and QLDPCs. And LDPC is used even in 5G. So I'll hand over to Radhika, who is a BITS Pilani Hyderabad faculty, and she has been in the previous PQC also. She described about the various coding techniques for MLKEM. So I will hand over to her. She is a excellent. She has done her learning at IIT Delhi, and she is currently teaching various faculty in the various students and PhD levels people in the area of math and quantum fluid dynamics specialization. So she's highly mathematical understanding is there. So let me pass on to Radhika. Are you there?
Yes, Professor. Thank you so much. Let me just start this one introduction to this. We have understood that some degree of error is unavoidable in the process of communicating. And as per this QKD specifications, this quantum bit error rates are expected to be less than 5%, as also mentioned by Professor Gokhale sir and sir. Right, so but that means that around 5 in 100 qubits can be at the most can prone to errors, and this error coding needs to correct in the sense that we expect around, I mean, the target is around 1 in 1,000 literally, so that is a possible error that can be accepted. Right, we have two popular codes to overcome the errors. The traditional LDPC, which is low density parity check, adapted to 5G and quantum, and now it's called QLDPC, and the other code is a CSS code. So the CSS is a stabilizer code, and we have separate parity check matrices for detecting X and Z type errors in the quantum system. Next slide, sir. So the math behind is very simple. We use only matrix theory to actually represent all this process. like how to detect errors and how to correct them. So that simple matrix theory helps us to do all this stuff. And we have special type of matrices here called sparse parity check matrices. And to represent these matrices or to visualize these matrices, we use what are called tanographs. And these tanographs are very useful, especially when we go for this iterative decoding. Next slide, sir. Right. So this sparse parity check matrices, as I said, these are the name itself indicates that they are sparse in ones, in the sense that we see a lot of zeros in these matrices. And these matrices are represented using what are called as stanographs, where the different nodes are nothing but the column heads, and the different C nodes. We have two types of nodes here called V nodes and C nodes. V nodes will be the different column heads of the matrix, and C nodes will be the different row heads of the matrix. And wherever there is a 1 in the matrix, the corresponding nodes are connected. So that's how we represent a tenor graph. And this tanograph is a special type of bipartite graph. And if you see, the figure shows a nice example of how a bipartite graph would look like. We have two different sets. The right hand side of the graph shows two sets, AC and BD. These are the two different sets, and the graph would be in such a way that the nodes of the different sets are only connected. We don't have a connection between the nodes of the same set. So such type of graphs are called bipartite graphs, and these graphs play a very crucial role in this LDPC or QLDPC algorithms, especially in the decoding process. So what are the different parameters we have in these codes are N, which stands for the total number of physical qubits, and we have K representing the logical qubits, and D is the code distance. So these are the three parameters we have in these LDPC codes. Next slide, sir. Yeah, now I'll take up a very small example of encoding the digit 6, encoding the sense, encoding as well as transmitting and decoding. So that's a process that we are going to take up now. Let us have a 4-bit representation of this digit 6, which is O double no. So that is a 4-bit information. We can also represent this 4-bit information in terms of 4 qubits, where I used a very normal technique. I should say a basis encoding technique, a very straightforward technique to convert or to encode bits to qubits. And suppose if I want to encode this information, the 4-bit information into a 7-bit information, say, then we will fix the parameter K as 7. And if I want to detect at least 2 errors in the final received message, say, so then we will fix D to 3. So it all depends upon the specifications, like what is the length of the code string that I want to send, which is K, and how many at most how many errors I can detect. So that is given by D. So here I have a nice matrix H. Of course, this is not a sparse matrix. Just for calculations, we've taken a very simple matrix. So this is a parity check matrix, right? And its columns are designated as C1, C2, and so on till C7. So the first row reads as C1 plus C3 plus C5 plus C7, right? So that is how we read the entries of this matrix. Now to find out the code word, we have to solve the system H into X is equals to, or H into C is equal to 0. So that gives rise to 3 equations that are shown on the slide. C1 plus C3 plus C5 plus C1 is 0, and so on. A very simple system of equations. As I said in the beginning, the mathematics behind this complicated theory is very simple. Simple matrices and system of linear equations. So now we just have to solve the system of equations, very straightforward, Gauss elimination or Gauss Jordan. Any of those methods will give us the answer, and the code word is presented here as the O1111T, transpose of it. That's what I mean when I wrote T there, right? Suppose after this code word is generated, it is transmitted to the other end, right? And suppose receiver at the receiver end, the vector turned out to be in such a way that there is a bit flip in the third position. So if you observe the previous code word and the receiver at the receiver end vector, you see that the third bit had a flip. So now how do I identify it? So we have, next slide, sir, please. So we have what is this, a syndrome-based decoding, where the syndrome is calculated by simply multiplying the matrix H by the vector R, the received vector, and that comes out to be, for this example, as 11, 0. Now, how do I identify the position? So this is 11, 0. I'll just go back to this matrix H and see which column reads this 110. So if you see, the third column reads 110 here, so which indicates that there is an error in the third position. So we'll go back and apply a NOT gate in the case of classical, and then we just have to correct the message. So this example has been demonstrated for a classical case. We can work on a quantum case as well, in which case we need to have two parity check matrices, Hx and Hz, right, to identify two errors, the two types of errors, the bit flip as well as phase flip. And we almost go along the same lines where we find out the code word, but this time we have to generate two code words, one which is a solution of hx into c is 0, and the other would be a solution of hz into c is 0. So we have two code words, and after that we again compute the syndrome in the similar fashion that we have done here. So once we understand what error we have, we apply the appropriate gates to get it. So in literature on QLDPC, we have several codes like the hypergraph product code or twisted product code bundle. There are several codes, and this one recent article on layer code architecture is one that we are presenting here. So this code basically takes a stabilizer code as an input, and it outputs a three-dimensional topological code. And the figure here, which is shown at the bottom of the slide, so we just, this is a representation of a three qubit repetition code with the stabilizer checks as ZZI and IZZ, and it involves 5 surface code layers. As you see here, there are 5 surface code layers. 3 surface code layers are for representing the physical qubit, and 2 surface code layers are used for Z-check. So the authors have demonstrated that this code exhibits a polynomial energy barrier. And yeah, next slide, please, sir. And they have also come up with timed bounds for the number of physical qubits, and also a lower bound for the code distance as well. Also, they compared the performance of their proposed model with the classical stabilized classical codes, stabilizer codes, and this what are these subsystem codes as well. So so the article can be seen in the reference there. That's all from my end. Thank you all.
Excellent. So we are just about exceeding the time, but I will go ahead with few Q&A, just each one of us starting. Vipin, are you there? Nikhil, are you there? So let's start with, anybody can answer. Okay, let's take these 5 questions before we come out. So why is QKD architecture technology neutral? Nikhil, are you there? Or anybody in the panel wants to answer? Go ahead. Okay, since nobody is answering, I will just answer it. You know that we have got like free space optical as well as we wanted to do optical. So if you have two different technologies and if you have to need to support both, then we need the architecture to be neutral. Then what infrastructure and software are needed to deploy QKD? Anybody there? Gokhale? Or
I
am
think
I?
enough was spoken about these two concepts by Nikhil and
Yeah, infrastructure and software. Yes,
yeah,
that's right.
yeah,
Yes.
right.
So we know that we have many ones. Like one we shared was from one was from the NIST statistical one to test, and the other one we had shared was of what is it? One of the Canadian universities had the 4 layers, and as Vipin mentioned also that there are many, and one thing is there is a lot of commonality between the 5G, like we have NOMA and orthogonal frequency division multiplexing. So all the software related to that, and NOMA, uh, which is again non-orthogonal mobile access. So there is parallel between the quantum QKD usage and telecom, and therefore the same thing happened in the case of what you call the last one, the code usage also. So you can see that industry deployments are based on the popular ones which Gokhale described. And why hybrid? Because we have to, you always do a NR first. That is, you call standard and non-standard. So first we have to do non-standard because already existing classical has to be combined to reach the ultimate goal of quantum. So we need to do hybrid before we can do. So these are the reasons. These were the questions we had framed. And now I will open the floor to anybody in the, what do you call, if somebody has any question, please, if you want to go, please, we can open your, what do you call the, yeah. Anybody there who wants to do the questions? I'll stop sharing. Yeah. Anybody, any questions? Are we, with this, we can end the call? Just wanted to. So what I'll do is I'll stop recording and then we can talk freely. So I am stopping the recording. Stop.